So far in these lessons, you've learned about two exciting groups of metals on the periodic table. First, there were the alkali metals, which are exciting because many of them, when you put them into water, they will fizzle, they will burst into flames, and they will explode. That's how ridiculously reactive that group of metals is. Next is the alkaline earth metals, which are exciting in their own way because they are metals that are used to build up the tissues of living organisms. Organisms are able to use them because they are reactive enough to form ions and be moved around in their bodies, but at the same time, they're not so reactive that they just explode on contact with moisture. And then the metals we're going to learn about today are called the transition metals, and they have their own set of unique properties that make them uniquely exciting in the periodic table. The first thing we're going to do in this lesson is we're going to consider the place of the transition metals in the periodic table. They occupy the center of the table. Here are the first 3 rows of transition metals in the periodic table. Now, as you think back to the metals that we've already learned about, you may have noticed that there was something in common between all of the alkali metals. They all shared a 1+ ionic charge. Same with the alkaline earth metals. They had something unique about them as well. The alkaline earth metals all shared a 2+ ionic charge. So what does that mean? Does that mean that the first column of transition metals is going to have a 3+ ionic charge to continue the trend? Well, actually, no. If you look at the periodic table on this page, the 3+ charge is above the column that contains the element aluminum. And then from there, the charges continue increasing. The next column has a 4+ charge. That includes the element tin, and then 5+, and then 6+. Now keep in mind, this little table is only showing you the positive charges that elements form. Keep in mind, a lot of elements form negative charges. But now, if the first column forms 1+, and then the second column forms 2+, and then 3+ is all the way over on the right-hand side, what about all of those elements in the middle? Now, it's important to separate something for you right now. The elements in the very middle of the periodic table, to the left of the line that I just drew over the table, those are actually the true transition metals in the rectangular block in the middle of the periodic table. The ones that are to the right of that line but still in the yellow section are known as the post-transition metals. Now, for this lesson, because we're just getting started with chemistry, we're just going to refer to these all as transition metals. And at the end of this lesson, you should see why we can group them together because they have one very important thing in common altogether. But the question still stands. What kinds of ions are these elements in the middle of the periodic table going to make? We're going to take a look at that by selecting several examples of the transition metal elements for us to look at. Let's take a look at the properties of these different atoms to try to get a sense of what the transition metals are like. First of all, it's important as we're thinking about the structure of the transition metals to realize how many electrons they have in their outer layers. Remember, the alkali metals all had 1 electron in their outer layer. Alkaline earth metals, 2 electrons in their outer layers. The transition metals can have anywhere between 1 electron on its very outside to 8 electrons on the outside that are available for bonding with other atoms. It changes from atom to atom. Look at these atoms, for example. Notice that aluminum has 3, manganese has 7 electrons available to bond. And while some of the atoms might be the same as others, they tend to have their own unique number of electrons that are available for bonding. That's the first hint at what the transition metals are like. Now let's take a look at what happens when the transition metals form ions. All I can say is that some or all of the outer electrons can be lost. For alkali metals and alkaline earth metals, I can tell you exactly how many. Where alkali metals, it was always 1 electron lost to form a 1+ ion. For alkaline earth metals, 2 electrons. For the transition metals, it's just some or all of them. Take aluminum, for instance. Now remember, aluminum was in that 3+ column of the periodic table, so we would expect it to lose 3 electrons and form 3+ ions. And it certainly does. In some periodic tables, at the bottom of the element square, it will show a bunch of numbers, and those numbers show the kinds of ions that that element can form. Aluminum is able to form 1+, 2+, or most of the time, because it's bold and big, 3 plus ions. Let's look at what that looks like on our aluminum atom. As you watch what happens, 3 electrons fly away from the aluminum atom and it forms a 3 plus ion. That's what we would expect for an element in the 3 plus column. But what about some of the elements in that rectangular center section? Well, take a look, for example, at manganese. Manganese is right in the middle of the periodic table, and it can form a ridiculous number of different ions. Most of the time it forms 2 plus by losing 2 electrons, or 4 plus by losing 4 electrons. Even sometimes it can lose all 7 of its outer electrons and form a 7 plus ion. And actually, this is fairly common for manganese. But notice it could also, under some conditions, lose 1 electron, 3 electrons, 5 electrons, 6 electrons. It can also gain 1, 2, or 3 more electrons to make a negative ion. So do you see how these elements are pretty unpredictable based on their place on the periodic table? Like, we don't know just because of where manganese is what kind of ions it's going to form. Let's look at another element. This time we'll take a look at copper. Now, copper is interesting because it actually only has 1 electron in its way outer shell. 1 electron that looks like it would be available for bonding with other atoms. There are many elements in the transition metals that have 1 electron in their way outer shells. Now, for the alkali metals, remember, 1 electron on the outside was extremely reactive. However, because the transition metals have more protons compared to the distance that 1 electron is away, it's being tugged harder by the nucleus, and these elements just aren't all that reactive. When copper forms ions, though, it not only loses that 1 outer electron, but it tends to lose 1 more of its inner electrons to form 2 plus ions. Zinc is a lot more straightforward. Zinc, if you look at the picture, has 2 outer electrons, and it tends to lose both of those electrons in forming ions to form a 2 plus, even though it could sometimes, under some conditions, form a 1 plus. The next element has its own unique properties. It actually doesn't have any electrons in the same outer shell that all of the other transition metals have electrons in. Palladium is unique among all of the transition metals, but that's kind of what we're seeing. The transition metals tend to have their own unique individual properties that can't just be predicted from their place on the periodic table. So palladium is a really stable atom that doesn't like to bond at all, but when it does, it either forms 2 plus ions by losing 2 electrons, or 4 plus by losing 4 of its electrons. And then tin, which is way over in the 4 plus column on the periodic table, we would expect it to form 4 plus ions, but it can also form 2 plus by losing 2 electrons, 4 plus by losing 4 electrons, or even 4 minus by gaining 4 extra electrons. And that's one of the characteristics that makes the post-transition metals unique, is a lot of them are able to form negative ions sometimes by gaining extra electrons. You need to understand that in the transition metal section of the periodic table, you can't predict the ions that are going to be formed just from its position on the periodic table. Now, that doesn't mean that scientists don't know why these atoms form the ions that they do. Scientists have studied all of these individual atoms and did a lot of math with them and figured out why exactly it is that they form 2 plus or 4 plus or 7 plus ions. And it all makes sense. It's just that you can't predict what the ion charge is going to be based on its position on the periodic table. Some other things that you should know about these elements, because of the way that their electrons behave, they are fairly unreactive. They have really big nuclei compared to the distances that the electrons are away from the nucleus. And it's not always easy for the elements of transition metals to form ions. Therefore, you can find transition metals in nature in their pure form often. We oftentimes will find native copper that's just copper metal pure in nature. Aluminum as aluminum pure in nature. We also find copper bonded to other things and aluminum bonded to other things. So sometimes they'll form ions and bond. Sometimes they won't. We call them fairly unreactive because of that. The transition metals also generally have very high melting and boiling points. The post-transition metals are actually much lower than the transition metals. The elements in the very middle of the periodic table tend to have the highest boiling and melting points of all. And then finally, the transition metals have the exact same properties that all metals on the periodic table have. Good conductors of heat and electricity. You can pound them into flat sheets. They're generally shiny. A lot of them are silvery and shiny, but you get a lot of other colors in the transition metals as well. And the transition metals tend to have a fairly high density to a very high density compared to other elements on the periodic table. So, in the previous lessons, we've learned alkali metals, very reactive. Alkaline earth metals, fairly reactive. The transition metals are fairly unreactive, and unlike either of the metals that came before, elements of the transition metals form unpredictable charged ions based on their position on the periodic table. And not only that, many of them can form more than one kind of ion depending on the conditions and what they're bonding with. So now you know a little bit more about the transition metals in the periodic table, probably the most common metals used in structures and technology in everyday life.